I'm Bruce Bugbee, president of Apogee Instruments, and this is a series of seminars on principles of environmental measurement. I'm not sure what number we're on, but today we're going to talk about photosynthetically active radiation. And to me, every single component of this is critical to understanding plant growth. This is one that I've been particularly involved with for a long time in my career, and I want to give credit to Mark Blomqvist, who is the chief scientist at Apogee. He and I have worked on this together for more than 10 years, refining this measurement and understanding its effects on plant growth. So let's get started with this. The first thing we want to look at is what I consider to be the 8 cardinal parameters for plant growth. So what are these 8 parameters? So here we have a plant, and we always want to show the anatomically correct roots of this plant. Well, let's take the below ground parameters. First of all, we have nutrients. That's 1. Second, we have water. Third, we have oxygen. Three parameters below ground that are critical to excellent plant growth. How about the ones above ground? Well, we have temperature, and I'm going to abbreviate that temp. We have humidity. So 1, 2, 3, 4, 5, not necessarily in order of importance. Carbon dioxide, critical parameter. 7, wind. We got 8. We're missing 1. The elephant in the room is radiation. And I'll put that in a giant box up here. We can measure all of these parameters better than the plants can sense them, but in the case of radiation, the plant is so exquisitely sensitive to that our best sensors are only equal to what the plant sees. So I should put some arrows here for radiation coming in. And specifically, today, we're going to talk about photosynthetic radiation, a subset of this. But I put this slide in here to really emphasize how critical it is to do radiation. All of these sensors, we can tell temperature by what's cold, it's warm. We can feel the soil for water. We can tell if it's high humidity. We think we can tell temperature, or we can tell radiation, but our eyes are a terrible light meter. Our irises contract when we go out in bright sunlight, and we don't realize how bright it is. They come back inside, they expand. We have a very poor ability to tell the amount of light, and the result of that is, I'm going to draw another little figure here. Here's our plant outside. Now we get that same plant, and it looks like this. Tiny leaves. People say, oh, your plant must be low on potassium. It is low on light. And anytime you have indoor plants, you really need to understand radiation. So I can't emphasize more the importance of really understanding that. So let's take a look at this. Multiple sources of lights to measure plants, right? We have the sun here. These are different types of electric lights. High pressure sodium, ceramic, metal halide, compact fluorescent, all with different colors of light. And there's a whole body of studies about what's the right color of light for plants. I'm not going to go into that, but our research says there's not as much difference as you might think among colors of light. But we're missing one key color on here, and that is LEDs. Light-emitting diodes. This is a picture of some plant growth chambers with different colors of LEDs. There's a tremendous amount of research going on with colors of LEDs, and people are using them for plant growth. So now look at a sensor has to integrate all these different types of light and accurately predict radiation for plant growth. And that's the focus of this seminar. How do we do that? What are the options for doing that and making accurate measurements of this so we can predict the rate of plant growth? All right, so a couple of definitions. First, and these are confusing to a lot of people. PAR is photosynthetically active radiation, and that just means the radiation that drives photosynthesis. UV light, that's radiation, but it doesn't, plants filter that out. It doesn't result in photosynthesis. Near infrared light doesn't have high enough energy for photosynthesis. This is the radiation for photosynthesis, and we'll come back to this again. It's 400 to 700 nanometers. That this is close to the visible range as well, what our eyes see. That's the radiation that drives photosynthesis. All right, second definition. Photosynthetic photon flux, or photosynthetic photon flux density. Now these two things refer to the same thing. In the next slide I'll explain the use of these two terms. This is the whole amount of radiation, again between 400 and 700 nanometers. So really all of these terms refer to the same thing. They're all this radiation that drives photosynthesis. These terms here are technically a little more exact, and ppf and ppfd. So we get then to what's a quantum, and this gets back to Einstein and quantum physics. A quantum is a mole of photons, and this mole is Avogadro's number of photons. So it's these particles coming in, and we know from the Stark-Einstein law that one photon excites one electron, and that's the first step in photosynthesis. So we're really interested in measuring with these moles of photons, and that's what the sensors measure, and we'll talk about that in the next slide. But quantum sensor then is a sensor to measure all this stuff. So that's when we say quantum sensor. We could say a PAR sensor, we could say a PPF sensor, PPFD. They're all the same thing, but that's where this word comes from, a quantum sensor. Or if the sensor is connected to a meter, then it's a quantum meter. And I'll show you some examples of that. In fact, let me show you an example right now. Here is a quantum meter, sensor plus the meter, and reads out all by itself. You can buy just the sensor and hook it up to a data logger, and then it's a quantum sensor. That's all it means between the two of those definitions. All right, now I want to talk about this issue of flux, and I've given myself a nice whiteboard to do this. Flux, if we talk to our physicist colleagues, flux has two definitions. And you would think by this time in the evolution of science, we'd have this term all worked out. One definition is per time. And in the case of photosynthesis, this would be moles, M-O-L-E-S, per second. That's one definition of flux, moles of photons per second. But equally valid is per area and time. Together, and this means moles per meter squared per second. Even in physics, these two things are used interchangeably. If we use this definition per time, we would have ppf, and then where's the area in here? Oh, we better add d for density to this definition to make sure we've got the area. If we use this definition and we said ppfd, well, wait a minute, we've got per area and per area again, so this d could be redundant, and we wouldn't need it. If you look through the literature on this, half of the people say ppf, and the other half say ppfd. The terms are used interchangeably. They mean the exact same thing. But it's been confusing to people, just as it's confusing to physicists. Is a flux only per unit time, or does it mean per unit area and time? There's the difference. For the purposes of this, we don't need to worry about it. ppf and ppfd are equal. All right, now let's go to what we're looking at. So here's photosynthetically active, photosynthetic photon flux density. It means radiation between 400 and 700. Sharp cutoffs. Now, remember that Stark-Einstein law that you're remembering for the test? Equal weighting of all photons. One photon excites one electron. Every photon coming in up here gets equal weighting on this chart. These are blue down here. This is ultraviolet. This is blue. This is green in the middle, and then red. And then right after 700, it's infrared, IR. Thermal radiation doesn't cause photosynthesis. It's just this here with equal weighting of photons. This is what we're after, a sensor that can get this. Sharp cutoffs on the end, so we can predict photosynthesis and plant growth by measuring this. All right, let's take a look at how we do this. Here is our quantum sensor that we just talked about. Very simple. One detector right here, one filter, and one output if we ran it over here to a meter. This is a quantum sensor. But this has to be designed with filters to get all of these colors exactly right. And that's a tricky business, very hard to do. If we make the jump to light speed, now we have a spectroradiometer and a prism. It breaks up the light, and we have lots of arrays down here. And this goes off to a meter. This is more accurate. It's also more than 10 times the cost. So we're going to look at these. How accurate are these compared to a spectroradiometer, and compare them back and forth. This is two options to do this: quantum sensor, spectroradiometer. Okay, here is what they look like. These are quantum sensors, one from LICOR, one from Apogee, and the Apogee spectroradiometer, a little bigger, a lot more stuff going on in here, but this has, if we did X-ray vision, we'd have a prism in here. The light comes in, it breaks the light up into multiple detectors down here, and these have a single filter. This, by the way, these are the most widely sold in North America, LICOR and Apogee. LICOR came out with a new sensor. They have a better head. It sheds water better now than this one, which tended to trap water. Oh, and it has a nicer cable, has a cable like this. But I'll talk about the new sensor and the old sensor. They're both equally accurate. It's just how it sheds water and how rugged it is for outside. So there's the comparison. About 10 times the cost for this. So if you need very accurate measurements, this is the instrument of choice. But let's talk about how close we can get with these. All right, here's our box again, equal weighting of photons. Kippenzonen is widely sold in Europe, and here's the LICOR, and look at how closely they match this curve. Now this is really good. Sharp cutoffs, because there's multiple colors of light. It's real important to have a sharp cutoff here. These are their two model numbers. There's the new LICOR, looks a lot like the old LICOR, and it's equally accurate to this. So now let's look at the original Apogee sensor that Apogee has sold for some time. Here's the curve. It comes up a little slow in the blue, and look how it cuts off here, at about 660, so it misses this radiation. That's not serious because it's calibrated to light sources unless you get a light source with a lot of radiation. Right here. Now let's take a look at an example of that. LEDs, they come into the picture. This is a red LED, and it's especially, it's called deep red because it's very close to this cutoff. I'm going to put deep red here. But this is common in some LEDs. And of course, this is a blue LED, but look at the problem. It cuts off before it can capture that deep red LED. So this is an excellent sensor for all types of light sources, except when there's a deep red LED in the light source. So what can we do about that? Let's take a look. This is the original Apogee. That blue line that we just looked at, Apogee developed a full spectrum a full spectrum quantum sensor. That's this gold line right here that cuts off here. So you can see the gold, the green, and the blue lines are all very similar, comes up better here. So if you need to measure red LEDs or LED spectra, this is better than the original, but there's the difference in cost for the full spectrum is about 2 times as expensive. So all of these are quite a bit more expensive than this, but if you measure in LEDs, you need them. So let's take a look at this. Here's the original. Black sensor, many people have this. Here's the new one. It's slightly taller, slightly bigger head. Because it's a higher end sensor, it's a gold color instead of a black color. That's what the two sensors look like, original and full spectrum. Now let's go back to that graph, and here's the difference again, right here. Now let's take a close look at the accuracy of all of these sensors. And to do that, we need to use this fancy integrated method originally developed in 1966, where it takes all the colors of light and it multiplies this by the accuracy of the spectral accuracies of these. And this is something that Mark Blomquist has done in great detail for all of these. And this is the equation to do it. I'm not going to go into that now, except let's look at the results. How close do we get? Kippenzonen, LICOR, and this is also the 190R, is very close to this. And then the original ORIG, Apogee, and the new, I'll put new right here, Apogee. Sunlight and cloudy, these are all tiny errors. So you really don't need the full spectrum to be accurate if you're just doing sunlight measurements. Any errors less than, certainly 1% are very tiny. Even 2% errors are fairly small for these. All right, now we take cool white fluorescent lights. All these errors, less than 2%, this is calibrated here. They're all calibrated to be 0. Small errors. Now, look at the original Apogee. Here's LEDs. Red and blue LEDs. Remember, it didn't capture that red peak? Big errors. If you're not using it under there, it's fine. But if you need these, you need full spectrum. And we jump to full spectrum and everything gets better. Metal halide a little better. High pressure sodium better. But these errors here in particular are small. And if you take a close look at this and pause this video and study it, you can see that the errors between Kippenzonen and LICOR and the full spectrum Apogee are all really small under all of these different types of light sources. This one is an asterisk because it has separate calibrations for sun and electric lights. That's explained on the Apogee website. All right, let's take a look at the next slide here. Oh, we need to go back one. Spectroradiometer, remember the 10 times big, more expensive? It nails every single source. 0 errors because it's measuring every color individually. So if you really need excellent accuracy, you need a spectroradiometer to do this. But most people, if they have 2 or 3% accuracy, that's good enough for their applications. Okay, so I'm going to conclude on this slide. Apogee also makes a line quantum sensor, and it looks like this. When we want to measure radiation underneath the canopy, it's really variable. There's bright light and shadows, so this sensor averages the light over the whole length of this. And if you start to cover some of these, it gives you a proportionately reduced reading. This is something that is helpful for people for transmitted light. And of course I have examples here hooked up to meters of the old, and I guess I should put them in the same order as this, but the old and the new sensors. Again, the new one is full spectrum and more accurate under all the different colors of light. So I hope this overview of some terminology and some differences among meters is helpful to understand and make more accurate measurements of photosynthetically active radiation. We look forward to another session on other topics in environmental biophysics. Thanks for listening.